nuclear fission. Nuclear fission really has had quite an impact on our world. Here's where it started. In 1939, these two German scientists, I believe this is Hahn here, yeah, name's right below it, and Strassmann here, were bombarding uranium samples with neutrons. So this is what they hoped to do. Take a neutron, send it flying into this unstable radioactive uranium, and make another isotope of it, make it uranium-236. But that's not what happened. What happened was they sent the neutron into the uranium, and they discovered that what they came out was smaller particles. And the weight of these smaller particles did not add up to the weight of the uranium in the first place. Now, they didn't quite realize what had happened yet, but Lisa Meitner, and I believe there's another scientist that I don't have a picture here, kind of figured it out once they saw the results. What Hahn and Strassmann had done, they had split the atom, and they were the first to split an atom. And this was in 1939 in Germany. And that date and that place will play a big role in what's going to happen 6 years later. But anyway, they had hoped to get the nucleus to catch one of these neutrons, but instead they were surprised to find the resulting nucleus was actually lighter. And they didn't realize that what they'd actually done was split the atom, and they actually did it with this contraption here that is in some kind of museum. You can see kind of behind it hints that it's in a museum. And you may wonder how you can take a neutron and send it at something. You know, with radiation and radioactive material, is kind of predictable whether you'll have alpha particles, whether you'll have beta particles, or whether you'll have neutron emission. So if you can take those particles that will have a neutron emission and send it toward these unstable particles like uranium, unstable nuclei like uranium, then you can do that, even though you are not physically touching the neutron. The reason I have the periodic table of elements here is because nuclei with 83 protons or more, and you probably can't see where 83 is, but 83 is right here. So if there are 83 protons or more, then every one of these is going to be unstable. It doesn't matter how many neutrons you have. If you have 83 protons or more, scientists have found out that you're just not going to have a whole lot of stability. Now down here in the bottom part, all those in the red, which you'll find out later is the actinide series, all these in the red are included, and one of those is uranium. Uranium right here is 92. It's the highest one found in nature. All these that are higher than that are synthetic elements. But anyway, all of these are unstable. So you're not going to be able to split these little bitty atoms, these little bitty nuclei right up in here. What's going to happen is going to be with these unstable ones. Is where you're going to end up getting the fission process. Now, uranium can split several different ways, and you hear some what looks like complicated formulas, but the thing to look at is here's uranium, you've got the neutron that has come at it, and it has formed Ba, and I forget what Ba is, but it's over here. It's on here somewhere, plus Kr, which I'm pretty sure is krypton, which is right over here. So it actually forms two new elements, and importantly, it will have 3 extra neutrons with it and a bunch of energy. Now, this is not always into these 2 elements. Uranium can also split into xenon, and I believe this is strontium. Already mentioned the Ba and the Kr. It can split into, I believe this is cesium and rubidium, but every one of these has extra neutrons left and a whole lot of energy. And we're going to talk about not only these extra neutrons, but the effects of these energy. And you probably can figure out that I'm leading toward the atomic bomb. So, I bet you didn't expect this guy, Albert Einstein, to be up here. But he actually plays a big role in this. Each dividing nucleus releases a lot of energy. In fission, the mass decreases because the missing mass has converted to energy. Now I think I will slide back to this one before here. Yeah, whenever I mentioned earlier that this stuff didn't weigh as much as uranium. It seems like with the law of conservation of mass that it would, but it has actually turned into energy. And that's the physics here. You have solid particle which has turned into energy. And like I said, that doesn't happen unless you have the instability. So there is actually a formula to explain the proportion of energy to the amount of mass. And that's what Einstein's formula was. E equals mc squared, and I hit the wrong slide there, E equals mc squared. Now Einstein had actually come up with this formula before Hahn and Strassmann, but he would play a part during the late 30s and early 40s. But here's what E equals mc squared stands for. E is the amount of energy. Mass is the amount of mass like in the uranium nucleus. And C is a constant for speed of light. The speed of light is a huge number. In fact, you can see it nearly 300 million meters per second. Light is incredibly fast. But if you were to square such a huge number, it doesn't matter what you multiply it with. Even if it's something with an itty bitty mass, you're going to end up with a lot of energy. If you have something that has the mass of 1 kilogram, just 1 kilogram, and you multiply it times this number squared, you would have like, well, I think I have it in my notes here, it would be the chemical energy of 8 million tons of TNT. I mean, you really have the potential for a lot of energy here. But in nature, this really doesn't happen. You really have to kind of force the splitting of the atom, and it's only going to happen under certain conditions. Under ordinary conditions, matter is very stable and just doesn't convert to energy. And even with all those unstable atoms like uranium, the mass that is lost, which is called the mass defect, that is the mass that would be lost and put in the formula here, is not going to be that large. But when it does get large, that's when you have the possibility of atomic bombs. You see, whenever Hahn and Strassmann first tested this out, they just discovered that it happened, had a lot of energy with it for what they thought would be a lot of energy. But what happens if you take that one uranium, split it? You may remember from what I said before, when it splits, it's going to have other neutrons with it. If you stack up a bunch of uranium together, and you split this atom, those other neutrons will go toward other nuclei of uranium, and split them, and split them, and split them, and you have just an incredible chain reaction. And that's when you really get a lot of measurable energy. And that's exactly what happened. In 1945, the United States dropped 2 atomic bombs. And Einstein, from what I understand, actually played a role. He was the one, he and some other scientists, wrote letters to United States President Franklin Roosevelt telling them what was being worked on in Germany. So as a result, the United States got to working on it, and they were the ones that figured out about the atomic bomb before Germany did. And here's a picture of a mushroom cloud that you get with an atomic bomb. So let's explain how this atomic bomb works. Here's the atomic bomb known as Little Boy. You have this uranium-235 bullet. What that is, it's going to have that neutron in it. Uranium-235 will have that neutron emission that we've mentioned. And you have this explosive which will send that bullet of uranium, you might say, toward a cylinder target. Now, what's in this target is a mass of uranium. I think they will call it, I'm looking in my notes here, they call it the critical mass. What the explosive does, it detonates all the uranium and pushes it toward this mass of uranium here. So that's when you get that nuclear chain reaction. You may remember in that chain reaction, one nuclear fission reaction can quickly produce 3, then 9 reactions, then 27 reactions, and so on. And that is the principle behind the nuclear bomb. On Hiroshima, the United States dropped this bomb, and 43 seconds after it was dropped, it was still in the air, they detonated this explosive. So that way it got close to the ground, and right before it hit the ground, I'm talking like a few hundred feet before it hit the ground, is whenever that exploded and released all that energy. And that's where you end up with the mushroom cloud, and you had just mass devastation. It killed from anywhere from 40-something thousand to 90-something thousand people right then. Well, anyway, it's not just bad things that nuclear fission is used for. Nuclear fission can be controlled, and you may remember back in 6th grade learning about nuclear fission, how it can be controlled into making electricity. I mean, you can control to some degree that chain reaction and how much energy is released. So as a result, you'll get nuclear power plants like this, which have nothing to do with making bombs. It's just a matter of a different way of getting electricity. So what about fusion? Well, fusion is a whole different ballgame. We have not been able to recreate the fusion like we see from the sun. Well, first of all, let me explain what fusion is before I tell you how it's related to the sun. Fusion is when you have very light nuclei. Thank you. When you have very light nuclei combining to form a heavier one. You know, in fission, you had a real heavy nucleus in that uranium-235. But anyway, fusion is really light. Fission is really heavy. In the sun, this happens. Hydrogen nuclei combine to form heavier nuclei. Let's take a look right here. So here's where you have that fusion of hydrogen. The hydrogen and hydrogen get together. Now that doesn't happen very often. It takes a great amount of energy just to get these hydrogens together because they're both positively charged. They're both positively charged. That ion, it makes an ion, and the electron tends to leave it. So it takes a lot of energy to get those hydrogens together. And since the sun and other stars have that much energy, that's where the fusion process takes place, on suns and stars. So that leaves us with hydrogen 2. Now that hydrogen 2 is called deuterium. That's an isotope of hydrogen. So that hydrogen 2 will then combine with another hydrogen, a regular hydrogen, to make an isotope of helium. So you have the change from one element to the next. And it kind of gets a little complicated. The helium and then we'll get together and have another isotope of helium plus more hydrogen, which sends out more of the reaction. But the big thing here is this. You may remember that this is the symbol for gamma rays. And that's what happens when the sun sends out energy. That's kind of the secret of the sun's energy. And you can kind of see where it's got all the deuterium and the helium isotopes there. But the big thing is nuclear fusion is how you can get so much energy coming from the sun. Well, I hope you have learned a little bit about fission and fusion.